The pigeonhole principle. It's a principle that seems almost too trivial in nature to be useful, however it's an incredibly powerful result that can be applied to some very interesting problems. In this video we're going to explain what the pigeonhole principle is, then we're going to look at 3 problems. The first of which involves proving that at least 5 people in London have exactly the same number of hairs on their head, and the last problem is quite a cool one. It involves n dimensions, integer coordinates, and yeah, that one's easy to explain on the whiteboard. So let's get into it. Okay, so what is the pigeonhole principle? The pigeonhole principle says that if you have more pigeons than pigeonholes, and pigeonholes are just places where pigeons live, if you have more pigeons than pigeonholes, then at least one pigeonhole has at least 2 pigeons in it. Okay, so no matter how we place those pigeons into the pigeonholes, at least one is going to have at least 2 pigeons. Okay, so we could put pigeon 1 here, pigeon 2 here, pigeon 3 here, well then pigeon 4 has to go somewhere else. Well, let's try a different rearrangement. So how about we put pigeon 4 in the middle one as well? Well then, already there's 2, okay? The problems we're going to see later, the main task is finding out what are the pigeons and what are the pigeonholes. Basically, we're going to have problems where we want to categorise a certain amount of things into different categories, but we have more things than categories. So, at least one category has more than one thing in it. Now let's have a look at the generalised version of the pigeonhole principle. Okay, so if we have, I'll go to black, if we have, and these pens are so hard to take off, if we have n objects, let's not call them objects, let's call them pigeons. If we have n pigeons, and let's say we have k holes, and k holes, then at least one hole has at least, okay, so we take n, we divide it by k, and then we take the ceiling. Okay, what do I mean by ceiling? Okay, the ceiling means you take this number, n divided by k, and whatever it is, you just round up to the nearest integer. Right, we have the ceiling of n divided by k pigeons. And try and think about this yourself. Try and imagine, having a set amount of things and a set amount of holes, and try and place those things or those pigeons into the holes, and you'll see that this really does make sense. Okay, this is quite an intuitive result. So for our first problem, we're going to show that at least 5 people in London have exactly the same number of hairs on their head, and we're going to do that using the pigeonhole principle. So, 2 facts. First fact is, in London, the population is about 8.9 million, and the average number of hairs on someone's head is 100,000. Okay, so what are our pigeons and what are our holes? It would make sense in this case for our pigeons to be everyone in London that we're trying to place in these categories. Well, what categories are there? What are these holes? The holes are the number of hairs on the head. Okay? Well, how many holes are there? So it says that the average is 100,000, but that's just the average. That's not the maximum or anything. So let's just take a rough guess at the maximum. Okay? Assume that, well, I think 1 million is a pretty safe guess, but just to be even more safe, let's just assume that no one in London has more than 2 million hairs, which is a very, very safe assumption. So max, I'm just going to write max hairs is equal to 2 million. Okay, well now we have our holes and we have our pigeons, so let's apply the generalized pigeonhole principle to say that, well, okay, so we're going to take the ceiling of what? Okay, so the number of objects that we have is 8.9 million, and then the number of holes that we have is now, let's say it's 2 million, and it doesn't matter if the maximum is less, because it just means that, maybe no one's in the 2 million, and maybe no one's in the, the 1.9 million hole, and that's fine, that doesn't matter. We can still apply the principle. So then divide 8.9 8.9 million, but of course the million's going to cancel, by 2 million, and this is going to be 4 point something, but because we're taking the ceiling, this is going to be equal to 5. Therefore, at least one hole, at least one specific number of hairs on heads, this hole has at least 5 Londoners in it, which in our case were our pigeons. Okay, so I didn't write too much down for this. I don't want to make it too mathematically laborious. But yeah, there we are, done. Okay, so the next question we're going to be considering is, can 10 people socially distance in a square room that's 18 meters squared? Well, first of all, what do I mean by social distance? I mean that all of them are maintaining 2 meters apart, right? So let's draw the diagram. We have a square room like this, and the area is 18 meters squared. So the side lengths are going to be the square root of 18. 18 is nothing but 9 times 2, so we have 3 times the square root of 2 here. And then, well, what do we have? We have 10 people, and I'm predicting these are going to be my pigeons, so I'm going to use black pen for this. So we have 1, 2, 3, 4, 5, 6, 7, 8, maybe there's one creepy guy in the middle, 9 and 10. Okay, so we have 10 pigeons. Well, I predict these are going to be our pigeons. So we want 9 or less holes. Well, how can we create 9 holes or 9 categories? Maybe one neat way would just be, let's just divide the bigger square into 9 equally sized smaller squares. And these are supposed to be equally sized, it's not the best drawing. Well, now what do we see? Well, we see there are 2 squares, there's at least one square that has at least 2 pigeons in it. Okay, so if we were to apply the generalized pigeonhole principle, we'd have 10 for our number of pigeons, divided by 9, which is 1 point something, and then we take the ceiling of that. So the ceiling of 1 point something is just 2. Okay, so we've established that at least one of these smaller squares has at least 2 people in it. Well, now let's consider what's the maximum distance that those people can maintain inside that square. Okay, well, the maximum distance is going to be across this diagonal. If they were both at the corner, that's the furthest they can be away from each other inside a square. Well, the side length of this smaller square is going to be a third of 3 times the square root of 2. So that's going to be square root of 2. And then by Pythagoras' theorem, we have the hypotenuse is going to be 2. So at most they can maintain 2 meters apart by both being on the corner. So you might argue, yes, if they're all on the corners. However, personally, I don't agree with that, because most people, at least the average person, is slightly thicker than a one-dimensional point. So even if they were on this cross-section here, well then, some part of the body is not going to be exactly on the cross-section, so 2 people will, at least 2 people will always be less than 2 meters apart. So to answer this question, we write a big fat no. This problem is slightly hard to understand at first. A diagram will definitely help. So first of all, in n dimensions, how many coordinates at integer locations are required for at least one midpoint to also be at an integer location? Okay, so this is a picture in 2 dimensions. And by the way, this is the problem I actually got in my Cambridge interview. So that's quite interesting. And we're considering the midpoints. Okay, so what do I mean? So we take any 2 points, we connect them, and then we consider the midpoint between those 2 points. And we want to know, well, how many points are required for at least one midpoint to also be at an integer location. Okay, in 2 dimensions it turns out to be 5. Okay, well, here's a better diagram to explain what I mean. And we're going to pose the question, well, why does this happen in 2 dimensions? And this will help us generalize to n dimensions. Okay, so we have points, let's call it A1 and B1. And let's say this is the point star. I'm going to denote this as star. And then we also have the point A2 and B2. and I'll denote this as a little arrow. And then we want to consider, well, how do we ensure that the midpoint between these 2 points is also an integer? Okay, well, how would you define the midpoint? So the midpoint of star and our little arrow, the midpoint of these 2 points is defined to be, well, you just take the average of the x coordinates, and you take the average of the y coordinates. So you add them together and divide by 2, add them together and divide by 2. Okay, so this is the midpoint. And how do you ensure that this is an integer? Well, in order for this to be an integer, a1 plus a2 has to be even. Okay, because we're divided by 2, so we want this to be an integer. So this has to be even, the numerator, and this numerator has to be even. Okay, consider when this happens. So consider when, we have 2 numbers, and when you add them together, those are even. Okay, remember we're only considering integers. So when you add 2 integers together, you can check this. We require the integers to have the same parity. And what do I mean by that? I mean that they both have to be even, or they both have to be odd, like this. Okay, even plus odd is odd. Okay, so we have to have this. And this has to be true for the b and the 2. They both have to be the same parity. Okay, well, in this case that makes sense. So if you look at these 2 coordinates, it's 2 and 6. Those are both even, of the same parity, and we have -1, that's odd, let's say. Well, it is odd. And then we have 1. So those are of the same parity. Okay, so let's consider the possible pairings of parity. So in this case, the x coordinate's even and the y coordinate's even. In this case, the x coordinate's odd and the y coordinate's odd. And let's list all the possibilities. So we either have even, or we have odd, or we have both even and odd. But then there's 2 ways to do this. We can have the x coordinates odd and the y coordinates even, or we can have the x coordinates even and the y coordinate is odd. Okay, so in 2 dimensions, there are 4 possible pairings. Okay, well then how does this help, and how is this related to the pigeonhole principle? Well, if we have 5 points, then at least one of those points has to be in one of these categories. Okay, at least one of these categories, these parity pairings, as I'm going to call it, has at least 2 pigeons or points in it. Okay, so there's at least 2 points which are in the same category of parity. Therefore, we have something of the form, for example, say they're both in this one. Okay, we have 2 points of the form odd, odd, even, and then we have another point that's odd, odd, even, and then when we take its midpoint, well, the x coordinates have the same parity, and the y coordinates have the same parity. Therefore, by the working out we did here, the midpoint is also going to be an integer location, because, well, the x coordinates add to an even number, and the y coordinates add to an even number. Okay, so now let's consider in n dimensions. Okay, well, how many of these pairings do we have? These parity pairings? Well, in 2 dimensions we had, okay, the x coordinate could be even or odd, the y coordinate could be even or odd, so we have 2 possibilities for the x coordinate, 2 possibilities for the y coordinate, so altogether we have 2 times 2, which is 4 possibilities, 4 pairings of parity. We call it n dimensions. You have these integer coordinates, and they have dot 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 dot. They have n ordinates, they're called, which comes from the word coordinates. So altogether we're going to have 2 times 2 times 2 times 2 n times. So we're going to have 2 to the n different pairings of parity. Okay? So we have 2 to the n pigeonholes. Well, how many pigeons do we need? We just need at least 1 more for at least 1 pigeonhole to have at least 2 pigeons. Okay, so let me write that down. We need, that's supposed to be B, we need just 2 to the n plus 1 points by the pigeonhole principle. So by the pigeonhole principle. And I'm not going to write it out in full, but yeah, that's the idea. In n dimensions we need 2n plus 1 points. Okay, so that's the end of the video. If you did enjoy, please subscribe. Check out the watermark that I made recently. I don't know which corner it's in. Just click that and subscribe. If you have any suggestions, please leave them in the comment section. And yeah, thank you for watching.